We are going to study titration in this video lecture. Now, titration would be used for preparing a soluble salt from soluble reactants. So, in your equation, your reactants and your products are going to be soluble. They're all going to be in aqueous state. They're all going to be solutions. So, you wouldn't be able to use excess method because excess method required an insoluble reactant. So, this is a method that would only be used in this special case where you have a soluble salt and your reactants are also soluble. One example, very common example, is you have NaOH. So you have NaOH and it's reacting with HCl. And the product that's going to be produced is going to be NaCl plus H2O. And remember, NaOH group 1 compounds, they're all soluble. So this is going to be in aqueous state. HCl is an acid, it's also going to be in a solution. So it's going to be in aqueous state. And NaCl is also a group 1 salt. It's your normal table salt. It's also aqueous. And H2O is the liquid which would be dissolving, in which all these substances would be dissolved. So H2O is in liquid state. So this is your reaction. Now we're going to try and prepare NaCl. We're going to try and prepare NaCl using. Let's try and use the previous methods that we did. Now what we can do is we can go to a lab and we can take a beaker. So let's say this is my beaker. And what I'm going to do is I'm going to pour some NaOH into it. And NaOH is a solution, it's an aqueous solution. And I'm going to pour some HCl into this container. So HCl is also an aqueous solution. So I'm going to pour those two things in the solution, and the substance that's going to be formed is going to be NaCl plus H2O. Now there's one problem, and that problem is that if you look at the equation, and this is a balanced equation, what you'll see is that one molecule or 1 mole is going to react with exactly 1 mole. So the ratio in which HCl and NaOH react, that's 1:1, which means that if I have 1,000 molecules of NaOH, I would need 1,000 molecules of HCl to exactly react. Now, when I'm in the lab, I can't really count how many molecules there are. I can't even measure the volume because let's say I have a smaller beaker of NaOH over here. And it's full of NaOH, but the thing is it's a dilute solution. So if it's a dilute solution, there will be fewer particles. On the other hand, if I take a beaker of HCl, now I know that they react in exactly the same amount. If I have 1,000 molecules of NaOH, it's going to react with 1,000 molecules of HCl. So I'm going to take another beaker of let's say HCl. Now this HCl might be very concentrated. I'm using exactly the same amount, the same volume of both solutions. But the thing is, this solution might be too concentrated, which means that the number of particles per unit volume is a lot. So there's no way of actually counting the number of molecules. Although there are ways, you can use stoichiometry, but that's going to be a very lengthy method. You need a very quick solution. You don't need to do a lot of calculations to actually figure out how you're going to add exactly the same amount of HCl and NaOH. So if you go into the lab and you don't want to do a lot of calculations, so without doing calculations, you would not be able to figure out how many molecules of NaOH are in this beaker and how many molecules of HCl are in this beaker. So if I mix these two beakers up, this is a lot more. You can look at the number of particles. There are a lot more HCl compared to the number of moles of NaOH. So HCl would be in excess. So HCl would be in excess. So what's going to happen is that your product would be contaminated by the leftover HCl that was because you added too much HCl. The reverse could also be true. What you might do is that you might end up adding too much NaOH. Now, if you add too much NaOH, then your product is going to be contaminated with NaOH. So there's no way of actually knowing, because all of your reactants and products are soluble. So there's no way of actually separating the excess HCl or the excess NaOH that you've added. In the previous case, we were able to filter it out because it was a solid, it was an insoluble reactant. But in this case, if I add too much NaOH or if I add too much HCl, then the product that would be contaminated, it would be impossible to separate that excess HCl or excess NaOH that you've added. So the first task is that what you'll do is you have to figure out a method, and you're going to try and add exactly the required amounts of reactants so that none of the reactant is in excess, so that your product is not contaminated by excess reactants. Because since all of them are soluble, it would be impossible to separate those reactants from your product. So I hope you get the point clear. So the purpose of titration is that you're going to try and add exactly the same amount of NaOH and the same amount of HCl, so that none of the reactants or products are going to contaminate your reactant. So there's going to be no leftover HCl or NaOH in your beaker. There's only going to be NaCl and water. So you have to somehow devise a method where exactly the same amount of HCl and NaOH are added. So in the next step, we're going to figure out what titration really is. In this lecture, I'm going to explain now how titration is going to work. And you've already, in the previous lecture, I've explained why when you have soluble reactants and your salt is also soluble, then adding one reactant in excess would contaminate your salt, and it would be impossible to separate a soluble reactant from the soluble salt that you have formed. So our task in this case is that we want to add exactly the same amount of NaOH and HCl, so that when a product is formed, it would have all the HCl and all the NaOH should react with each other, and there would be no leftover reactants. Now, this is a rough diagram for what a titration experiment is going to look like. What's going to happen is you have a burette, and burette has these tiny graduations. You can measure very tiny volumes using burette. And there's a tap at the bottom. You can open the tap and you can close the tap to add whatever required amount of reactant you want. So we're going to add one of the reactants in our burette. For example, in this case, you can pick any reactant. You have two reactants. One is HCl and the other one is NaOH. So you can pick any reactant. There's no rule for picking which reactant should be part of the burette. So let's take NaOH. Now, I've filled this burette with NaOH aqueous, and what I'm going to do is I'm going to measure. Let's say this is my starting point. I fill the burette till this mark, which is generally the 0 centimeter cube mark. So I filled the burette to this mark. So that is my starting point, and I'm going to put HCl in the conical flask at the bottom. So I'm going to put HCl in the conical flask. So there is HCl aqueous at the bottom of the conical flask. The equipment that I'm going to use to fill HCl is called a pipette. What a pipette does is that it's like a dropper, and a pipette generally measures. I mean, you're going to fill this pipette till this mark. There's going to be a mark, and generally it's 25 cm cube. The common laboratory pipette has a 25 centimeter cube volume. There's a suction device at the top, so it's like a dropper. So there's going to be a suction device at the top, which is going to suck the liquid of HCl out of the container that it's been part of, and you're going to use it as a dropper and place this HCl in this conical flask. So it's used as a dropper. You can Google videos about how a pipette works or functions, and you realize that it's simply a device for putting a liquid from one container or transferring a liquid from one container to another container, and it's very exact, it's very accurate. So you fill this pipette to this 25 centimeter cube mark, and then you release all the liquid into this conical flask. So that's how a pipette is going to work. Now coming back to titration, you have two reactants. One is NaOH and the other one is HCl. Now what I'm going to do is I'm going to open the tap. So this is my tap over here. So I'm going to open this tap, and NaOH from the burette would start falling into the conical flask drop by drop. Now this burette is going to release NaOH very slowly. It has a very small opening, and it generally adds NaOH drop by drop. So slowly NaOH would start falling into the HCl, and they will start reacting. And they will start forming NaCl and water. So that's your reaction happening. So NaCl plus H2O would start forming. So gradually all the HCl would react, and it will get converted into NaCl and water. Now what's going to happen is that initially your flask only had HCl in it. So at the very beginning of the experiment, the pH of your flask is going to be almost around 1. It's going to be very acidic. HCl is a strong acid. So let's say the pH is around 1. And as soon as NaOH starts falling into this conical flask, this HCl is going to get used up. It's going to start reacting with NaOH. It's going to start forming NaCl and water. So your pH would gradually change. NaCl is neutral. It's a salt. So salt have neutral pH. So NaCl is going to have a pH of approximately 7. Now, this pH would gradually change, and it would be converted into 7. But if I don't stop the tap, if I don't turn this tap off, and if I keep on adding NaOH, then eventually what's going to happen is that NaOH would go in excess. All of the HCl would get used up. And once all of the HCl in the conical flask gets used up, then all that NaOH that's falling into the conical flask, it will have nothing to react with. So the salt that is produced, and if I don't turn the tap off, then that NaOH would keep falling into the product, and it would contaminate the product. Now NaOH is alkaline. It's an alkali. So my pH would gradually climb to 13 because of this excess NaOH. So my task is, the way I'm going to figure out that my reaction is complete. So my task is that I'm going to try and stop at this point. I need to stop at this point. If I can figure out a way of stopping at this particular point where the pH is almost 7, then I would have figured out a way of not adding NaOH in excess, because if NaOH goes in excess, then my pH climbs to 13. And if I add too little NaOH, then the HCl would not get used up and the pH would be acidic. So I need to add exactly the right amount of NaOH where the pH becomes exactly 7. That means there's no excess HCl present, there's no excess NaOH present. All of my reactants have been used up, and my pH is going to be exactly 7. So the first thing to figure out when you're doing titration is, or if you want to do titration, is you need to figure out a method of measuring pH. And the method of measuring pH is, you're going to use different indicators. You have litmus paper, you've or probably have already heard about litmus paper. We need a method of measuring pH. Litmus paper or litmus solution. So we have different indicators that change color with different pH. So in acidic conditions, this is red, and in alkaline conditions, this is going to be blue. The second indicator that we can use is called Methylorange. It's red in acidic, and it's orange, yellow, so it's also a solution. So it's going to turn orange yellow in alkaline conditions. The third that we can use is called Phenolpthalein. Which is colorless in acid, and it would be pink or purple in alkaline conditions. Then you have universal indicator as well, but the most commonly, so there are many different indicators. You can look up my worksheet, my data sheet on my website. There's a list of different indicators given. Now, the most commonly used indicators in titration are Methylorange or Phenolpthalein. So what I'm going to do is, before starting titration, I'm going to add a few drops of. So I'm going to add few drops of let's say Methylorange. Now, if I add a few drops of Methylorange, what's going to happen to the colors of this solution? Now, initially, I had only HCl in this conical flask before I started adding NaOH. Now, HCl is acidic, so Methylorange would give a red color. So, initially, Methylorange is going to give a red color, so my solution would be red in color. And as I keep adding NaOH, then that NaOH reacts with HCl, forms NaCl plus water. And if I add one tiny extra drop of NaOH, the pH goes to 13. And the color in alkaline conditions is going to be orange, yellow. So at what point should I stop the titration? Now this color change would be very abrupt. So I'm going to keep on adding anyways. My tap is on, and as soon as my color switches from red to orange yellow, that would indicate that I've added too much NaOH, and that is the point where I need to exactly stop my tap, or I need to turn off my tap. So if I turn my tap off exactly at the right time when the color is changing, then I would stop at exactly this point, which is where pH is equal to 7, where the solution only contains NaCl and H2O. So that's what titration is. I've explained it in detail. I'm going to go through this one more time. What I did was I added NaOH in a burrette on top, and I added HCl in the conical flask, and I opened the tap, and NaOH started dropping in small amounts into the HCl. So initially the pH was around 1 because this flask over here contains only HCl, and as NaOH drops into this conical flask drop by drop, then they react and they form NaCl and water. And since it's a salt, its pH is almost equal to 7. And it's neutral. But if I keep on adding NaOH, now HCl is used up, so that NaOH has nothing to react with. So my product that is formed is going to be contaminated by NaOH. And if I keep on adding NaOH, the pH would go to 13 because NaOH is a strong alkali, so the pH rises to 13. So my point is that I need to somehow stop at pH 7. So what I do is I add any of these indicators. There are many indicators available. There are different types of indicators. The most common ones are Methylorange and Phenolpthalein. So if I add Methylorange, initially this flask had acid in it, so it was red in color. And as soon as if I add too much NaOH, that NaOH makes it alkaline, the color is going to change to orange yellow. So my exact point of turning off the tap is that as soon as the color changes from red to orange yellow, that means that I've added too much NaOH. That is the point when I need to stop the titration immediately without adding too much NaOH into my products. So this is the point where I'm going to stop the titration. And the last thing that I'm going to do is I'm going to note down the volumes of NaOH used and the volumes of HCl used in the titration, and I would know exactly what amount of NaOH and what amount of HCl should I mix. So once I know that, I'm not going to do the titration this time. What I'm going to do is I'm simply going to take a beaker, fill it with the exact volume of NaOH and with the exact volume of HCl. This time I'm not going to add Methylorange because I already know the volume that is going to be used. So what I'm going to do is I'm going to simply mix them up, and I'm going to get NaCl and water. I'm going to get a pure solution of NaCl and water without adding too much NaOH or without adding too much HCl. I'm going to now describe a step-by-step method of answering a question related to titration in your exam. For example, if somebody asks you to prepare pure dry crystals of NaCl, so what are you going to write? The first thing that you're going to write is the first point that you're going to write in that question. It's going to be a 4-5 mark question. Sometimes it's a lesser mark question, so you need to write fewer points. But if it's a 4-5 mark question, then you have to describe the whole experiment in detail. Now, the first step you're going to describe is you're going to fill the burette with NaOH. So you fill the burette with NaOH aqueous. Once you've done that, the second step would be you're going to fill the flask with the other reactant, which is HCl. And remember, NaOH, it could be the other way around. You can fill the burette with HCl and you can fill the flask with NaOH. So it could be the other way around as well. So I have filled the burette with NaOH, and I'm going to use a pipette to fill 25 cm cube of HCl into the conical flask. So what you're going to write is you're going to pipette 25 cm cube of HCl in the conical flask. Once you've done that, the other step would be that you would have to put a few drops of an indicator solution. So you're going to put a few drops of indicator solution. That indicator could be Methylorange or it could be Phenolpthalein. These are the most commonly used indicators. And in the previous lecture, I've already told you what the color change is going to be. So in this particular experiment, I'm adding a few drops of Methylorange indicator. Add a few drops of Methylorange indicator to the conical flask. Once you have done that, you're going to start the titration now. So the third point is you start the titration. So start titration and you add NaOH drop by drop. So you start titration, adding NaOH drop by drop. Drop by drop. And once you've started, the indicator is going to change color. And since it's acidic at the beginning and it's going to become alkaline when excess NaOH is added, so the color change. So you're going to stop the titration. Stop titration when the color changes. So stop the titration when the color changes. And in the case of methyl orange, it's going to be red in the beginning, and it's going to turn, when the NaOH is in excess, it's going to turn orange yellow. So the color changes from red to orange yellow. So that's your third point. Once that happens, the fourth point would be that you note down the volumes that you've used. So now you know, you don't know, initially you didn't know what volumes to use. But once you have performed the titration, you would know that a certain amount of NaOH is going to react with a certain amount of HCl. So note down the volumes used. So you note down the volume of HCl and NaOH used. Once you've noted that down, you would know, okay, what amount of HCl and what amount of NaOH are going to be mixed. So you repeat the experiment, because right now your solution is contaminated by methyl orange. So you've added methyl orange, you can't take it out because it's also in solution form. So what you do is you repeat the experiment. Without indicator. So you repeat the experiment without indicator, and whatever solution that is formed is going to be pure NaCl solution. So, but that's a solution. And if they are asking for a pure dry, if they are asking for pure dry crystals, so what you're going to do is the last step would involve crystallization. So the fifth point would be about crystallization. You would have to crystallize the solution to get crystals of NaCl. So you're going to describe crystallization in detail in the last step, and that is that you evaporate the solution to crystallization point. So evaporate the solution to saturation point. And once that has happened, you're going to cool gradually. Cool slowly or cool gradually. That would allow crystals to be formed, so that particles of NaCl get together and they start forming large crystals. So you cool gradually and filter out any crystals that are formed. So you filter out any crystals formed and dry between pieces of filter paper. Between pieces of filter paper. So that is your last step. Now, these are 5 steps that I've written down. You can, depending on the question and depending on the size of the answer required, if it's a 4 or 5 mark question, it would be better that you write all these points. Remember, crystallization is a very important point, because most of the time they ask for pure dry crystals. So you have to describe crystallization in detail. You can sort of shorten the other points. For example, what you can say is you can simply just tell them that you fill the burrette with NaOH, then you pipette 25 cm cube of HCl in the conical flask. You don't need to mention the color change of the indicator. You just add a few drops of indicator, then you start titration and you stop when the color changes. And if you're using a particular indicator, you might as well tell what the color change is going to be. And you note down the volumes, you repeat the experiment, and the last step is crystallization. So you can consult the marking scheme. I've written down the 5 steps in detail. So depending on the question and the size of the answer required, or the marks of the related to the question, write an appropriate answer, but always check the marking scheme for if there are any points that are more important than the other points. I am now going to do another example of titration, and this time I'm going to take another reaction. I have potassium hydroxide reacting with sulfuric acid, and it's producing potassium sulfate and a water molecule, and all of them are aqueous. So whenever when my salt is soluble and my reactants are also soluble, I'm going to use the titration method. And again, I'm going to take a burrette. So I'm going to take a burrette, and I'm going to take a conical flask. And what I'm going to do first is, the first step would be that I would fill this burrette with sulfuric acid. I would take one of my reactants and fill the burrette with sulfuric acid. It could be KOH as well, so there's no rule for what goes into the burrette. It could be any one of the two reactants that you have. So I'm taking H2SO4, which is an aqueous state. It's a solution. So I'm going to take H2SO4 and fill my burrette with H2SO4. So my burrette would be filled with H2SO4, and I'll note down the starting volume, the start point of my burrette. So the first step is you fill the burrette with H2SO4. in aqueous state. And remember, the question would precisely be that in your exam, the question that would come on this would be that you would have to prepare pure dry crystals of potassium sulfate. So I'm going to describe a method for preparing pure dry crystals of potassium sulfate. So that's the first step. Fill the burrette with H2SO4 aqueous. And the second step is going to be that I have this conical flask. So I'm going to use a pipette which measures 25 cm cube volume. So I'm going to use a pipette, and I'm going to put KOH aqueous. So KOH would be in aqueous state. So I'm going to put this KOH aqueous, 25 cm cube of KOH, into this conical flask. So I'm going to use a pipette. So I'm going to pipette 25 cm cube of KOH aqueous into a conical flask. The third step would be that I would put a few drops of indicator solution into this conical flask. So it could be any indicator which I've described previously. So in this case, I'm using phenolpthalein as an indicator. So I'm going to add a few drops of phenolpthalein indicator in this conical flask. So few drops of phenolpthalein So I'm going to put a few drops of phenolpthalein in this conical flask. So your third step would be add a few drops of phenolpthalein indicator in the conical flask. Now, if you remember, phenolpthalein has a specific color. Phenolpthalein is going to be pink initially. So it's going to be pink initially because KOH is present. It's an alkaline solution. So in alkalis, phenolpthalein is pink in color. So phenolpthalein is going to be pink in color. So the fourth step is, what you're going to do is you're going to start the titration. You're going to start adding H2SO4 drop by drop slowly into the conical flask. So you start titration by adding H2SO4 drop by drop. Now, when you are adding H2SO4 into KOH, what's going to happen is, when you're adding H2SO4 into KOH, what's going to happen is that the solution in the flask is going to be, it will slowly convert into K2SO4, because KOH is going to react. It's going to end up reacting with H2SO4, which is coming from the top, and it will be converted into K2SO4. So slowly your solution would be turning into K2SO4 aqueous. So it will slowly turn into K2SO4 aqueous, and at one point all the KOH would get used up, and once all the KOH has gotten used up, if you still continue to add H2SO4, then that H2SO4 would have nothing to react with. So the solution would have excess H2SO4, and once you've added excess H2SO4, the solution would become acidic, and this pink color would turn into, this pink color that you had initially would turn into colorless, because phenolpthalein is colorless in acidic solution. So what you're going to do is you're going to try and precisely stop at this particular point. Initially you had KOH in the flask, it was pink in color because phenolpthalein was added. Phenolpthalein is pink in alkaline solution. As soon as you started adding H2SO4, that KOH would slowly get converted into K2SO4 aqueous, and once you've added excess H2SO4, that is when all the KOH has been used up and all of it has been converted into K2SO4. And if you still continue to add H2SO4, then that H2SO4 would be in excess. It would have nothing to react with, and that H2SO4 would make the solution acidic, and the phenolpthalein in the solution, the indicator in the solution, would give a colorless, it would change into colorless from pink, and that would be an indication that it's in excess. So that's the point when you're supposed to stop. So you're going to stop exactly when the change is happening, when it goes from pink to colorless. So let's complete our sentence, our description. You start titration by adding H2SO4 drop by drop, and you stop titration when color changes from pink to colorless. Pink to colorless. That would indicate that the salt that is produced is K2SO4. It's mostly K2SO4, so you didn't add a lot of excess H2SO4. Only a one tiny bit of excess H2SO4 is going to make it colorless. So that's the point when you're going to stop exactly. So you repeat the experiment 3 or 4 times until you get an average reading. So you note down the volumes. So the next step is note down the volumes used. Note down the volumes used and repeat. Without indicator, because the indicator is contaminating the solution. So once you know how much sulfuric acid reacts with how much KOH, you don't need to add the indicator anymore. So you're going to note down the volumes, and you simply repeat the titration using the correct volumes that were recorded in the previous titration. So note down the volume used and repeat without indicator, which in our particular case is phenolpthalein. And the last step would be that your solution is K2SO4 aqueous. So you would have to produce crystals of K2SO4. So the last step is crystallization. So the last step is crystallization, which has to be described in detail. So you evaporate the solution to saturation point. Evaporate the solution to saturation point or crystallization point. Then you cool gradually. and you filter out any crystals that are formed, and filter out crystals formed. And then you're supposed to dry those crystals, so dry them between pieces of filter paper. You dry crystals between pieces of filter paper. And that completes your description of this titration. And remember, crystallization is an important point. You can summarize the above points, but never miss out on this crystallization part, because that's very important. Most of the marking scheme questions require that point. So whenever you attempt a question, please have a look at the marking scheme and how it's answered. If it's a 4 or 5 mark question, or if it's a 3 mark question, some points would be left out, some detail would be missing. But it's a good practice that you mention all the details so that you don't lose marks anyway.